Hello and welcome to a tutorial on the topic of similar figures. And it's helpful if you've managed to watch the tutorial on volumes prior to this, because in that tutorial I really stressed the importance of thinking about the number of lengths that you need to calculate areas and volumes. Namely, that when you calculate the area of something, you will always be multiplying two lengths together. And when you calculate the volume of something, you will always be multiplying three lengths together. And in fact, that is the concept that underpins this really very neat bit of maths under the heading of similar figures. Let me motivate it with an example, and then we'll do some slightly more complicated examples. It's best taught, I think, by example rather than using sort of general ideas. So let's imagine that we had a rectangle. And let's imagine that we don't know everything about this rectangle, but what we do know is that it has one length is, let's say, 6 meters. So this might be like a plot of land for a garden or something. And let's say we also know the area is, let's say for the sake of argument, it is 30 square meters. Okay. Now, let's imagine now that we have what's called a similar rectangle. And similar means that the rectangle has the same aspect ratio, the same shape, but a different size. Okay. So it's not the same size as the first rectangle. You can see it's bigger, but that the ratio of the width to the length is the same, even though we don't actually, prima facie know the width of this particular rectangle. We could work it out, but we're not going to bother doing that. What we're told here is that the length of this rectangle is, let's say, 10 meters, and we're asked to find the area. Now, this is a neat method that you don't need to do very much work here. As long as you're told that these figures are, and the formal word is similar, this is a bit like the sort of thing you can do, with Photoshop or something like that, where you can sort of expand or reduce images. It's almost like someone's taken a photograph of the original piece of land and simply magnified it. So what we define is sort of a number akin to magnification. We talk about it as a scale factor. We say that there is a constant factor which relates this length to this length and relates this length to this length. And that scale factor we can determine by just dividing 10 by 6. That's, as it were, the magnification. The scale factor relates to what you might call a linear dimension, namely one dimension. I want to call this scale factor little h. Now, the rule that you have to sort of remember here, although it's very intuitive, is that the new area, so let me call this rectangle 1 and rectangle 2. Let's say that A1 is 30 and this A2 is what we're trying to determine. So the area of the large rectangle is going to be the scale factor h squared times the area of the small triangle. And that scale factor is 10 over 6. And so the 10 over 6 is 5 over 3. So the area of the large rectangle will be the scale factor squared times the area of the small rectangle. And I can just work this out very quickly here. So I have 5 divided by 3 all squared multiplied by 30, and I get 83.3 square meters. So that's an example of similar figures. The key thing is, first of all, you must be told that these are similar, namely that one is as it were a magnification of the other with no distortion. Then if you're given enough information from the first, and all you need actually is, in 2D, is to know the area and one length, then you can work out the area of the second figure, so long as you know its linear dimension by working out this scale factor. Okay, let's do another example. Let's say we have, let's go from big to small this time. So let's say that the first thing we're given is some funny shape, like looks like a sort of an artist's palette or something. But let's say this is an architectural sort of plan for a pond or something like that. And what we're told is the area. So we're told the area of this is 10 square meters. And we're given the linear dimension. We're told the width of this funny shape from here to here is, I don't know, let's say it's 5 meters. And then we have the same shape but smaller. Okay, not quite sure why someone would want a pond this tiny, but let's just say now that this has been shrunk all the way down to 1.5 meters, okay? And the question is, what's the area? Now, it would be very hard to calculate the area from first principles because it's a funny shape. You know, you'd actually need the methods of calculus that I mentioned in the last volumes tutorial to work that out. But we have enough information here because of similar figures to work out this other area. We want to work out the scale factor from sort of the old to the new. In this case, it's getting smaller. This is the new sort of figure. It's 1.5 divided by 5. The scale factor is a ratio of the two length scales that you have to hand. And let's again call that h. And then the new area will simply be h squared times the old area. So we have 1.5 divided by 5 all squared times 10. And let's see what that equals. 1.5 divided by 5, that's sort of the reduction. And then that's multiplied by 10. Oh no, I have to square it. 1.5 divided by 5 squared times 10 is 0.9. So that new sort of pond, as it were, would be, maybe that would be for sort of inside some kind of fancy apartment, is less than a square meter. Right, let's just do one more example, but now we're going to go to 3 dimensions, okay? And it's exactly the same idea. You just need one spatial dimension, but the difference in 3D compared to 2 is that when you're working with volumes, it will be the scale factor cubed, okay? So let's deal with a cone. That's a nice 3D shape. Let's imagine we have quite a big cone here. And then we have a significantly smaller cone. But crucially, it has the property of similarity, namely that the kind of aspect ratio between the height and the base is the same. So this is rather a sort of a squat cone, and so is that one, and they are similar. You know, similar sort of sounds like it's roughly, but mathematically the word similar means that they're identical except for size. Okay, that's the meaning. So, let's say for this big cone here that we say knew the radius of the big cone. Let's say the radius is I'm going to say 4 kilometers. Why not? Not quite sure what the application is here, but never mind. It's 4 kilometers, and the volume is, let's say, I've got to try and make up a reasonable number given the shape here. Let's say it's 30 kilometers cubed. Okay, and all we're told about this smaller cylinder is that it has a radius of, let's say, 2 kilometers, and we have to calculate the volume. All right, so we calculate the scale factor, and scale factor is the new length scale, as it were, the length scale of the figure that we want to calculate something of, divided by the length scale of the figure where we're given information. So 2 divided by 4, obviously that's just 0.5, and let's call that h again. Now the volume of the cone number 2, this is really important now, is h cubed times the volume of cone number 1. So when you're dealing with volumes, you cube the scale factor. When you're dealing with areas, you square the scale factor. So the volume of the second cone is h cubed times the volume of the first cone. That's 0.5 cubed multiplied by the volume of the larger cone, which is 30. So let's just do that on the calculator. Being sort of lazy with the using calculator here, but it's just because generally these problems are set to you where you're expected to manipulate some perhaps slightly unwieldy numbers. So this is 3.75, and the dimensions are kilometers cubed. I'll let you figure out a sort of a reasonable application for that. You know, this could be like a model of cloud formation or something like that, you know. So it's not completely nuts, in fact, but yes, that could be an application. The key thing, though, is to see the method here, very, very powerful if you have this property of similarity, that you can work out areas and volumes from very little information if you know the area or volume of a shape along with one linear dimension. As long as you know the linear dimension of a similar shape, you can calculate its area or volume just by evaluating this scale factor. And again, just to be boring and repetitious, scale factor is squared when relating areas, and it's cubed when relating volumes. And that's because of what we've talked about many times, which is that areas are the product of 2 lengths, hence 2 factors of scale factor. Volumes are always products of 3 lengths, hence a product of 3 scale factors. They're h cubed. Good. So that's similar figures. I hope that's been helpful. And all that's left in this this series on what's in Scotland called the National 5 curriculum, but I think it's very similar to O-level or GCSE in the UK, which I think is similar to many other curricula for sort of high school children in the range 14 to 16 around the world. So the 2 topics left for us to cover are vectors, which will be 2 tutorials, and statistics, which will be 2 tutorials. And then we will come to an end for this particular curriculum. So I hope to see you for those last topics, and thank you, as always, for your patient viewing, and I do hope these are helpful. So see you soon.